Hello, everyone. Today we will be talking about um, our introduction to t-test. This week we are going to be covering this specific unit associated with t-test. We're going to be talking about independent samples t-test, and then we're also going to be talking about related samples t-test. I have uploaded on Blackboard for you 2 chapters to read rather than reading the chapters that are in your textbook. I find that the chapters in your textbook, I don't really find them too user friendly, and they probably are going to leave you asking more questions than what it is that you're probably going to get answered. But rather here, the 2 chapters that I've posted on Blackboard for you are from a supplemental textbook that I've used in previous semesters that I find to be very, very helpful in terms of explaining how to do t-test for independent samples and also for related samples. And they are also substantially shorter than the other chapters from your textbook. So today what I want to talk about is I want to actually talk about, in this particular lecture, independent samples t-test. I will be uploading another lecture for you, or it should already be up, that is going to be introducing the aspect of related samples t-test. So please do look first at this one and then look at the related samples t-test lecture later on. So in terms of our independent samples t-test, we are now moving on in terms of going from the descriptive location associated with statistics to now moving on to testing actual research questions. So in our previous weeks, we've really been talking about this issue of z-scores and talking about, okay, well, let's say for instance that the population average is X value and my sample average is Y value. Is there a difference between those two values if I look at it on a Z distribution? But now we are moving to asking more specialized questions in terms of our t-test, and we're really talking about looking at group differences. So rather than us saying, okay, we know what the population average is and this is what my sample average is, now I'm saying I've taken 2 samples from the population. Here is one group and here is another group, and now I'm comparing their scores. So ultimately what we're doing here is we're doing now kind of the next step in terms of the sequence of statistical analyses that we would want to do if we were wanting to compare groups. So what are we going to talk about today? We're going to talk about when it is that we would want to use a t-test and why it is that we would want to use a t-test, and then also what information is actually going to be given to us by the t-test. So before we begin, let's just introduce some very basic terminology. Now, we've already talked about some of this basic terminology in our previous weeks. We especially talked about it last week when we were talking about the aspects of power. And one of the things that we've talked about up to this point is we've talked about the different types of designs. Even at the beginning of the semester, I introduced this issue associated with different design types that we sometimes use in research situations. So one of the big distinctions that we're going to be making here associated with t-test is that we have 2 different types of t-test. One type of t-test is what we call an independent samples t-test. And then another type of t-test that we have is called a related samples t-test. So now, as you can imagine, in terms of the creative naming process of statistical analyses, why did we call one independent samples and then another one related samples? Well, because the independent samples one means that we have independent groups, and the related samples t-test means that they are related to each other. So the groups are actually related to each other. How are they related? Are they cousins? Are they siblings? No, they're the same individuals that we're using. So in an independent samples t-test, we're using different individuals in different groups, just like we've talked about with our between groups research design. So in reality, when we think about a between groups research design, from here on out, we're really thinking about the aspect of using something like an independent samples t-test. So this is really where an independent samples t-test is really going to come into play, because we're using different groups. So one individual is going to be in one group, and then we have another individual who's in another group. So what differentiates the 2 groups? Potentially a treatment. One group may be receiving a placebo, another group may be receiving the drug, one group may be receiving online study materials, another group may only have the textbook, etc., etc., etc. But here we have different groups, and here the big part associated with the between groups research design is that the key issue associated with them is that they can only participate in one group or one condition of my experiment. So only one group or one condition of my experiment. So in other words, these people cannot participate in the other group. They can only be in one group. So let's say, for instance, that we're looking at the difference between males and females. If we're looking at the differences between males and females, this automatically becomes a between groups research design. Why does it become a between groups research design? Because a male individual cannot participate in the female group and a female participant cannot be in the male group. Now, potentially, right, we could argue that, oh, well, what happens if they go through a sex change or something like that? Okay, potentially that may happen, but here we're assuming here that that's potentially not going to happen within the time frame of us collecting data. So here we're going to assume that these individuals are going to be mutually exclusive, that they're going to be in one group or they're going to be in another group. And that's the key issue here with the between groups design, that people are in one group versus another. Now, we also have the option of doing what's called a within groups research design. With a within groups research design here, we allow now participants to participate in more than one group of our study. And in reality, they participate in all groups of my studies. So in other words, they participate in all conditions or in all groups. Okay, so in other words, we allow these people to cross over to the other group. Now, does that mean that they freely cross over from one group to another and then back and forth, back and forth? No, absolutely not. Here, what we're doing with them is we say, okay, what we're going to allow you to do is we're first going to allow you to be in the group that receives, let's say, study course information online, right? So they're going to be in the online only class. And then what we do is we say, okay, now we have another group that they're only receiving textbook information. So after they're done participating with only the online material, now they move over and now they're in the other group where they only receive book information. And then we test them on the exact same information. So we test them to see if there's any differences between their scores in terms of performance. But here the key difference is that they're in both groups. So they were in the online study group. We tested them at that point, and now they move over to the other group where they receive only textbook information, and we now test them at that point. So here, the within groups research design is going to reflect what we're going to call our related samples. Okay, so our related samples t-test. So up here, we had our independent samples t-test, and now down here, we have our related samples t-test. And again, now what makes them related? That they're the same individuals. So the individuals in group 1 are going to be the individuals in group 2. Now, why would we want to use these different types of groups? So if you're thinking to yourself, okay, well, that's weird that you're using these different, situations. So why in one situation would you want to use it between groups, and then in another situation you would use it within groups design? Well, this depends a lot on the type of question that you're asking. So let's say, for instance, that we're looking at gender differences on motivation. Here, you're forcing yourself to choose a between groups research design. You cannot have a within groups research design comparing males and females because, again, the males can't cross over to the female group and the females cannot cross over to the male group if that's what you've stipulated as your requirement. And here, traditionally, we would say that these are going to be separate groups. So in that particular instance, we would assume that we have a between groups research design because we have mutually exclusive groups. But now what happens in the case where you say, okay, well, what I want to do is as a professor, I want to see how my students perform better. Do they perform better with only online material or do they perform better with the textbook only? So here, well, we test them first with only online material, and now we test them again with only using book material. So here you're having to compare the same individuals across time. Now in that specific instance, I wanted to know, and I specifically said, I want to compare my students who received online material and then also received the textbook material. But at the same time, I could have stipulated my question to say, well, I only want to compare individuals who receive online material and then have a completely separate group who receives only textbook information. So here, keeping them mutually exclusive groups, then in that instance, it would become a between groups design and not a within groups design. Now, are there benefits and limitations to using both types of designs or one versus the other? Absolutely. Remember when we introduced the issue of power, and I know right now you all are thinking to yourself, oh, I don't want to think about power, please, we just got done with all that stuff. I never want to think about it again. But unfortunately, this stuff is going to be coming up for the remainder of the semester. So when we thought about power, we said that one of these two types of designs had less error variance. So which of these two types of designs have less error variance? And remember, error variance is the differences between our scores that are not due to the researcher's manipulation or control. So in other words, potentially extraneous factors or other factors that may influence my scores that I'm not in control of. So again, of these two, which ones do you think has less error variance, within or between? And the answer is a within groups design has less error variance. Why? Because we're using the same participants in both groups. Okay, that's why we have less error variance, because we have the same participants in both groups. So here we assume then that you shouldn't drastically change from time 1 to time 2. So if you're in the first group and we're the online class only, and then we also put you in the textbook only class, right? So here the first part of the semester was only online, and now we're converting it to being strictly a textbook course, and we want to compare scores to how students are performing within the same semester. So here, I would compare your score to your score. You drastically shouldn't change within that time frame. So for instance, you shouldn't see that light at the end of the tunnel. You shouldn't potentially change religions. You shouldn't see or have an epiphany about what your life should potentially be, in this, moment of clarity or whatever the case may be. We would assume here that you would be very, very similar to each other from time 1 to time 2. Now, potentially there may be some minor differences, but we'd expect that the differences would be very, very minor and not really contributing too much to error variance. Still be there, but it's going to be minimum. But with the between groups design, we have lots more error variance. And why? Well, because if I'm comparing Susie to Alex, if Susie is in my online group and Alex is in my textbook group, now all of a sudden I'm comparing Susie's score to Alex's score. Well, what if they're just naturally different? So what if Susie is just a better studier than Alex is? So in the case of Alex, Alex studies 1 hour, Susie studies 15 hours. So Susie comes to class every single day, Alex only comes to class once a month, etc., etc., etc. So all those little tiny differences between the two individuals are ultimately going to contribute to error variance. So if Susie is in my online course, but Alex is in my textbook course, but he doesn't study as much as Susie, well, now I have another factor that I wasn't considering to potentially affect my performance outcome. So here we always do have to be considerate that whatever design we pick, there are pros and cons to all of them. And that's what I told you at the beginning of the semester. That was the punchline, that there is no one best strategy to use. So do you want to use an independent samples t-test? That depends. Why? Well, because it depends on the question that you're asking. Do you want to use a within groups design? Well, that depends. What does it depend on? Well, it depends on what your research question was. So if your research question is asking things like, are there differences between two different groups? And here you're assuming that they're going to be different individuals, so you're going to have groups that are mutually exclusive. You're going to want to use, in this particular case, so, depending again on our situation, depending on what this question is going to be, we are then going to select the appropriate design and we're going to select the appropriate statistical analysis. So, this is why one of the things that I've been talking about all semester is that it's so important to really stipulate what your research question is, because your research question will then drive what kind of design you're going to select, and then it's also going to drive what kind of statistical analysis you're going to select. This is why all semester long I've been trying to instill in you the idea that there is this integral match between research methods and statistics, that we really can't separate the two. It's unfair for me to come in and only talk about statistics and that's it, because research methods is going to influence statistics so much. So in other words, me picking the type of design here that I have in terms of a research situation is ultimately going to influence what kind of statistical analysis I have. So if you also think about when we talked about null hypothesis significance testing, that I said you calculate the inferential statistics that are necessary, so the one that you need to answer your question, not all of them, because the ones that are necessary are going to be the ones that your research design or your research question is asking you to calculate. So in our particular case, if we're comparing males and females on motivation, I need a between groups design and I'm going to use an independent samples t-test. I'm never going to use a within groups design and a related samples t-test because that's unnecessary. Now, what happens in the case where my research question is, well, do students do their performance change? Does the students' performance change from using an online platform to using only a textbook platform within the same semester? So here we're using the same individuals and we want to track them across the different groups. Here in that particular case, I want to use a within groups design and I'm going to end up using a related samples t-test. So it's very, very important to know what it is that we're already getting into. For our particular lecture, Today, in this one that I'm presenting for you in this video, we're only going to be talking about between groups designs, thus talking about independent samples t-test. Now, just some additional terminology to introduce at this point. We've talked about independent variables all semester long. Here, I'm talking about independent variables again, even though this is a research term that we normally encounter in a research situation. I still need to talk about it here because it's so important for us to understand this idea of statistics as well. With an independent variable, again, do not think that with an independent variable, we're always talking about the variable that we manipulate or that we control. Independent variables come in many different forms. Independent variables can be the one that we manipulate that can potentially be an independent variable, or it can potentially be the one that we examine or that we observe to potentially have an effect. So in other words, think of an independent variable as being your predictor. So here I'll write for you. So this is the predictor, or what we also call the influencer. Okay, so in other words, this is the variable that we assume is potentially going to have an effect on my dependent variable. Now here I say it could potentially be the one that you manipulate or the one that you just examine. So in other words, the one that I observe. Okay, now why is it that I make this distinction between manipulate and observe? Well, because in certain situations I can be in direct control, because that's what manipulate means. I can be in direct control of my independent variable. So for instance, think of like a treatment. So receiving a drug versus no drug. Okay? So here I can be in control of that. So I can give an individual a drug treatment versus not giving them the drug. I am in control of that independent variable. Now, in other cases, I am not in direct control of that independent variable, but I still want to examine its effect on the dependent variable. That's where we have things such as gender, smoking. Let's say, for instance, we have individuals who come in and we want to monitor their anxiety levels, or even, for instance, what languages do they speak. So here, I'm not in control of your gender. You can't come in, so I can't say to one of my students, let's say, for instance, Alex walks in, and I can't say to Alex, well, guess what, Alex? You randomly got assigned to the female group even though you're a male. And Alex says, but I'm a male. I don't want to be in the female group. I can't be in there. Well, too bad. Sorry, you're randomly selected to the female group. Well, no, we can't have that. So that's not going to happen in that particular case. So rather, Alex comes in and Alex says to me, hey, I'm a male. Perfect. You go into the male group. Now, are there going to be situations in a research setting in where somebody's going to come in and they're going to want to mess with you and they're going to just kind of want to lie to you? Absolutely. But you know what? We have to take what people tell us at face value to a certain degree. So if we have a participant who comes in and let's say, for instance, they are clearly male and they tell me I am female, I can't argue with them and say, no, 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 you look male. So you go into the male group. I cannot do that. If a participant comes in and they tell me I'm a female, I have to put them in the female group because that's what they wrote. Who am I to stipulate to them that what they are and what they are not? And I'm not going to be starting to tell them, okay, well, let me do a physical examination to check to really see if you are female or you really are male. Because again, if we think about, for instance, social psychology, this is such an important term that we think about, sexual identity. So if the person classifies themselves as another gender than what they are, who am I to say to them, no, you're not, I'm going to put you in this situation? If I'm concerned or I feel that they may come from a different population than the ones I want to sample from, I may just mark their data. So I may just flag their data and then make sure that when I'm analyzing my data, I may hold some of that data out. I may say, you know what, I'm not going to really include them because they may potentially become an outlier in some of my data, or they were potentially messing with me. I don't know. I'm more concerned about that at a later point. But during the experiment, I'm not going to say anything to them. Smoking behavior. Let's say, for instance, a person comes in and they say, well, I'm a smoker. And you say, okay, well, how many cigarettes do you smoke, in a 24-hour period? Well, I normally smoke about one cigarette a week, but I'm a smoker. Okay, well then you're going to be a smoker because that's what you're classifying yourself as. But now if I later on determine that people who are smokers are people who have to smoke 10 or more cigarettes in a 24-hour period, I can make that judgment call later on. But in this specific situation, the person comes in and they report how much it is that they smoke. Now, also, can I give people, nicotine, or can I give them a drug? Can I give them, cigarettes or alcohol? Potentially. I can potentially be manipulating that variable, but in most cases, I'm going to have to examine it and observe it. So, in other words, people are going to come in and I'm going to have to ask them to self report how much they actually smoke or how much they actually drink or if they consume specific drugs, because I'm probably not going to be able to give them those specific drugs. But in some clinical trials, I may be able to do that. Now, so even in other cases where we can have, for instance, somebody potentially coming in who has high or low anxiety, we may potentially want to say to these individuals, okay, you came in and you reported that you have high anxiety. We're going to put you in the high anxiety group. Individual comes in and they report that they have low anxiety. We automatically put them in the low anxiety group. Or, for instance, you may potentially want to manipulate somebody's anxiety levels. In this particular case, you can definitely do that. A person comes in, you start yelling at them, you have very loud aversive music playing, potentially giving them high anxiety. A person walks in, you greet them very cordially, you have them sit down in very comfortable locations, etc., and here that will produce potentially low anxiety. So in this particular instance, you could have a situation where you observe anxiety, that the participant comes in and they already bring their anxiety level with them, and that's what they report, and that's how we decide on what group that they're going to go in. Or we can manipulate their anxiety. But in other situations, I can't manipulate things like gender. I can't manipulate certain things like how much it is that a person smokes. I may not be able to do that. Or even identifying how much it is that a person has in terms of language knowledge. So I can't say, oh, you came into the research situation, you know English and Spanish. And if they tell me, well, no, I only know English. No, no, no. You know English and Spanish because that's the group that you got randomly assigned to. I'm in control of that. Well, no, that's not going to happen. We can spend months and years training them to get both of those languages so that now we put them in that language group, but unfortunately I may not be able to do that or have the time or resources to be able to make that kind of commitment to them. Now, our second issue here that we want to look at, or our third term that we want to identify here, is the issue of a dependent variable. Now, with the dependent variable, most commonly we call this our DV. Our DV is what we also call our criterion variable. So our criterion, or we also call this the influenced. And the influence or the criterion variable is essentially the variable that you measure the participants on. So this is going to be your performance assessment if you want to think about that. So measuring their GPA, their comprehension, their motivation levels, their self-esteem, looking at those potential factors. So for instance, if we were to make a research question associated with one of these independent variables and a dependent variable, remember that we always use the statement that I introduced to you at the beginning of the semester. And remember, you can always use the sentence. So the effect, here I forgot an E, the effect of the IV on the DV. Okay? So that's what we always want to look at, the effect of the IV on the DV. That's the order. We never put the DV and then the IV. So the DV never comes first and the IV comes second. The IV always comes first, the DV always comes second. So here, for instance, let's say the effect of gender on motivation. Okay, so gender would get plugged in here, motivation would get plugged in there. So in that particular case, my gender variable would be a observed independent variable because I am not in control of it. It's not a manipulated independent variable. My independent variable category doesn't change, so it's still an independent variable. It's just now called an observed independent variable, not a manipulated independent variable. My dependent variable then would be whatever it is that I selected to be. I'm going to measure them on their motivation, on their comprehension, on their GPA, on their self-esteem, on their self-worth, whatever it is that we want. But ultimately here, I want to measure them on this particular factor. All right, so now that we've covered some basic terminology here to set up our discussion associated with our t-test, let's now really start thinking about a situation in where we would want to have an example of actually using an independent sample t-test being used. So let's think of a situation like the following. What happens in the case where we would want to examine the differences in terms of performance between two groups? So here I want to compare two groups, and here I'm going to have two mutually exclusive groups. The two groups that I'm going to compare are going to be my smokers and my non-smokers. And here, again, these are mutually exclusive groups. So they're independent from each other. They are not related. So the people who are in group 1 cannot be in group 2. So I can't have people who are smokers and then be non-smokers, or non-smokers and then be smokers. I can't have that in my specific example. Now, potentially in a research situation that you may want to take people who are non-smokers and then give them cigarettes anyways to see if they smoke. That may be something different. But in my situation, all I'm doing is I'm asking people, do you smoke? Yes. Do you not smoke? Yes or no. All right. That's all we're asking in this particular case. So here, the smoking component associated with my research question, is there a difference between people who smoke and who do not smoke on exam scores? So here, the difference between people who smoke and who do not smoke. Is there a difference between smoking or not smoking on exam scores? What is this variable here of smokers versus non-smokers? Am I going to consider this to be my dependent variable or my independent variable? So again, the effect of smoking on exam scores. So within smoking, we're going to have smokers versus non-smokers. So here again, think of that order that I was talking about, the effect of the IV on the DV. So what comes first? The IV. So the effect of smoking or not smoking on exam scores. So here, the smoking aspect, so smoker versus non-smoker, this is going to be considered my independent variable. Now here, I'm not going to be in control of it. So this is an observed independent variable. In other words, participants come in and they report if they smoke or they do not smoke. If they smoke, we put them in the smokers group. If they don't smoke, they're in the non-smoking group. So here we want to evaluate if there is an effect associated with smoking or not smoking on exam performance. So in our particular case, our smoking or non-smoking behavior is going to be considered my independent variable. The exam scores, this is my performance assessment, this is what I'm measuring my participants on, is going to be considered my dependent variable in this particular example. So if we think about what the null hypothesis would predict and what the alternative hypothesis would predict, and also what my research hypothesis would predict in this specific situation, because remember, they're all different. These are different components. So my null and my alternative hypotheses, these are going to be statistical predictions. So again, these are statistical predictions. And the research hypothesis is a research prediction. So in other words, the research hypothesis is a prediction based on previous evidence. So in other words, other people have been doing research on smokers and non-smokers on other performance assessments, on other dependent variables, but they haven't done it on exam scores. So here, based on what they found in previous research, I'm now going to be drawing conclusions or making a prediction based on what they found now about my own particular study. So let's say, for instance, we find that people who smoke are more anxious than people who do not smoke. So here we would assume then that if people become more anxious as smokers, potentially they may become even more anxious on an exam. So an exam induces anxiety in certain individuals. Well, if the exam alone produces anxiety and people who are smokers become jittery already naturally because of their smoking addiction, potentially now we may have an additive component to their anxiety associated with their addiction, and now the exam produces even more anxiety, thus potentially decreasing their scores. So that may be something that we may say. So we may say smokers, okay, smokers scores will be lower than non-smokers. Okay, so non-smoker scores are going to be higher. So smoker scores are going to be lower than non-smoker scores who are going to be higher in this specific situation. So that's going to be my research hypothesis. So what is the null hypothesis going to predict about the difference between smokers and non-smokers in terms of exam performance? The null hypothesis, again, would predict, and here since we're comparing groups, we're looking at group differences, the null hypothesis is going to predict no difference. Okay? That's what the null hypothesis is going to predict. No difference or no effect. Okay? So no difference, no effect. Now, how are we symbolically going to state out the null hypothesis in terms of looking at our example for a t-test? Our null hypothesis is going to be symbolically represented like we have here. So remember that we have a sample average, right? So X bar or capital M. So we're going to have X bar for smokers. Okay, so that's my average for smokers. And then I'm also going to have my average for non-smokers. Okay, I'm gonna have my two averages. So what is the null hypothesis going to predict? The null hypothesis is going to predict that the difference between my smokers and my non-smokers, so if I look at X bar minus X bar, so the difference between smokers and non-smokers, the difference would be equal to 0. Okay, but since X bar represents a sample statistic, remember that I have to have a population parameter associated with it. So I'm going to assume here that whatever my average is for my sample for smokers, I'm going to have my population parameter of mu smokers. So I'm going to assume that in the population, all smokers are going to function exactly the same as my sample of smokers. So mu1 or mu smokers minus mu non-smokers is going to be equal to 0. Okay? Or mu1 is equal to mu2, which is equal to 0, or mu1 minus mu2 is equal to 0. So here we would say mu smokers minus mu non-smokers would be equal to 0, or mu smokers is equal to mu non-smokers, which is equal to 0. So here, replace that 1 and that 2 with smokers and non-smokers. That's what the null hypothesis would predict. And again, why am I using mu here rather than my sample average of X bar? Because remember, my population parameters are always in reference to the null and the alternative hypotheses, because these reflect the real world. Okay, so who is the real world? It's not my sample, it's my population. So since the population is reflection of the real world, here the values that we get from the population are going to be our parameters. So thus why we use here mu in our particular case. Now here, this is what symbolically is going to be stated associated with our null hypothesis for our t-test. Okay, very, very important for us. So it's essentially telling me that the differences between my two groups are not going to exist because the null hypothesis predicts that there's no difference between the groups. The alternative predicts the alternative of the null hypothesis, right? So it's going to predict that there is a difference. So there is a difference, or that there is an effect. So here it's going to predict that mu1 is not going to be equal to mu2, which is not going to be equal to 0. Sorry, that should be not equals to. Okay, so mu1 is not equal to mu2, and the difference between them is not equal to 0, or mu1 minus mu2 is not equal to 0. So in other words, in terms of my example, it's going to assume the following. Mu smokers versus mu non-smokers, the difference between those two groups is not going to be equal to 0, or mu smokers minus mu non-smokers are not going to be equal to each other. So mu smokers are not equal to mu non-smokers, and the difference between them is not equal to 0. Okay, that's ultimately what it's going to predict for us in terms of the alternative hypothesis. So my research hypothesis is that smokers and non-smokers are not going to be equal to each other. So I'm saying that they are different from each other. So I'm saying that smokers are going to perform worse than non-smokers. And here I'm going to assume that the difference is going to be a significant difference. Okay? So here we're starting to really use this term now of significant in terms of our discussion. So significant differences. So here we really want to make sure then that we're saying that the difference between smokers and non-smokers, it's not going to be small. We're saying it's going to be extreme enough for us to draw the conclusion that they are significantly different from each other. So ultimately here, what are we saying here with the null and the alternative hypothesis? I've predicted that smokers and non-smokers are not going to be equal to each other. So I'm predicting the alternative based on previous research. I could have predicted the null based on previous research if that's what previous researchers would have said to me. If previous researchers would have said, you know what, when you compare smokers and non-smokers in terms of their anxiety levels, they really don't differ. And then here, where it's like, well, an exam may induce a little bit more anxiety, but probably not sufficient enough for them to become more worried and perform at a lower rate. So here, I may have predicted then that smokers and non-smokers may have not differed. But here, that's just kind of up to whatever the research was saying. But here, I'm assuming that the research says that there is a difference between them in terms of their anxiety level. So thus, I'm assuming that since they're already different in terms of their anxiety level, the exam is going to induce even more anxiety in both groups, so thus it's going to create even more anxiety in smokers at a higher rate, that it's going to create lower results for them in terms of their performance. So here, I've predicted the alternative in my particular research hypothesis. So again, remember the null always predicts no difference. The alternative predicts that there is a difference in this particular case. Now, our statistic that we're going to be using this semester is going to be my t-statistic. Okay, so my t-stat. So what is the null hypothesis going to predict about the t-value? Just as with our z-value in our previous week's work, that we said z was equal to 0, now our null hypothesis would predict that t would be equal to 0. Okay? Why would the null predict that t would be equal to 0? Because essentially it's saying that the difference between the two averages is going to be equal to 0, and essentially here my t-value would then be equal to 0. When I show you the formula in just a couple of minutes here, in just a couple of slides, I'm going to show you why it is specifically that my value would end up being equal to 0, attaching it back to this issue of the null hypothesis. But here, for our purposes, at this point, just know that the null would predict that t would also be equal to 0. The alternative would predict what? So if the null predicts t is equal to 0, the alternative would predict that t would not be equal to 0. Very, very important, okay? So t is equal to 0, t is not equal to 0 in this particular case for the alternative. Okay, very, very important.
So for our specific example, we really do want to use an independent samples t-test to solve our question here that we had just set up. So again, remember, we're here trying to now compare two groups. Again, these are two mutually exclusive groups, and we're trying to compare them on their exam performance or their exam scores out of a possible 10 that they can get on the exam. Remember that our smoking issue, smokers versus non-smokers, this is my independent variable. My exam scores are going to be my dependent variable in this particular case, since that's what we're examining our participants on. So if we think about an independent samples t-test and what an independent samples t-test is really going to be doing for us, an independent samples t-test is really going to be useful for us since we have groups that are independent from each other. So in other words, we have groups that are going to be mutually exclusive. So that's really what the key for the term independent samples t-test really signifies for us. It really means this idea that our groups are different from each other, and they are different from each other in the capacity that they are different individuals per group. So in other words, the group of individuals that we have who are smokers are going to be different than the group of individuals that we have who are non-smokers. In other words, we have mutually exclusive groups. They are not related to each other in any capacity in terms of them being the exact same individuals. So ultimately here, what do we really need as a requirement to satisfy this condition that we are using mutually exclusive groups or a between groups design? In this particular case, we need to be able to have what's called a dichotomous variable. What does the term dichotomous mean for us in terms of statistics and in research? It means that we have, in this particular case, an independent variable that has two groups or two levels or two conditions. In other words, we have two groups in our particular case that we have smokers and non-smokers. What happens in the case where we would have a third group? Let's say, for instance, we have smokers, non-smokers, and moderate smokers. In that particular case, since we would have three groups, we no longer could use our independent samples t-test, because one of the key requirements associated with an independent samples t-test is that we, at maximum, can have two groups. And here, the requirement is that we specifically have two groups that we're comparing. What happens in the case where we were to have one group? Well, in that particular case, if you only have one group, you cannot use an independent samples t-test. You could potentially use something like, for instance, in your textbook, in one of the chapters, I believe it's chapter 9, the author uses what's called a one samples t-test. And in that particular case, you only have one group that you're comparing your value to for the population. But in our particular case, what we're now doing is we're comparing our two groups. So the requirement is that you're going to have two groups maximum and minimum that you're going to compare. And again, these groups have to be mutually exclusive from each other. If they are related to each other in any capacity, then you have to use a different statistical test. And in our particular case, we're going to be using our independent samples t-test because we're comparing these two groups, smokers versus non-smokers, who are completely mutually exclusive from each other. So in this particular case, what is it that we really want to do with an independent samples t-test? An independent samples t-test is going to be very useful for us when we're going to be comparing two groups, again, that are mutually exclusive, and you're comparing them on the same dependent variable. So let's say, for instance, you were going to compare smokers on their exam scores, but then you calculate for the non-smokers GPA. So exam scores and GPA are two very different dependent variables. So in that particular instance, you couldn't compare smokers versus non-smokers because you didn't measure them on the exact same dimension in terms of the dependent variable of exam scores or GPA. You're measuring them on different things. So it's, for instance, like saying, well, I'm going to compare myself to somebody who took a physics exam. Well, you can't really compare yourself to someone who took a physics exam when you took a stats exam, because they're very, very different things that you're comparing them on. But if you both took the psychology exam or you both took the same physics exam, then at that point, now it's okay for you to compare each other because you're comparing each other on the same criterion or on the same dependent variable here that we're talking about. So what is an independent samples t-test going to be used for? This is really the core associated with an independent samples t-test. An independent samples t-test is going to answer the following question. Do the groups significantly differ from each other in terms of the dependent variable? So in other words, does group 1 scores significantly differ from the scores from group 2? That's really the core question that we're wanting to ask ourselves. So in our particular case, what we're really interested in examining for our particular example is there a significant difference between smokers and non-smokers exam performance? That's really the question that we're asking ourselves. Now, whenever it is that we're looking at an independent samples t-test, there are some very basic requirements that need to be met in terms of an independent samples t-test for us to be able to use it. Now, if we don't satisfy these criteria, then we're not going to be able to select an independent samples t-test, but rather we're going to have to end up selecting some other type of statistical analysis. Now, one of the first key requirements that we have associated with an independent samples t-test is that whatever it is that we're comparing our participants on, so the dependent variable has to be quantitative in its nature, so it has to have a numerical value. I cannot do any type of statistical analysis on words, and that's a very, very important thing that we always have to consider in terms of statistical analyses, because in many instances, as researchers in many instances will collect data that is in narrative form. So in other words, they don't actually collect numerical data. Rather, what they're going to collect is they're going to collect verbal responses from participants. So one of the first things that they in that instance have to do is then convert all the narrative responses or the words that were given by the participants. They have to convert them to numerical form so that way they can actually conduct statistical analyses. Without that procedure, they're not going to be able to conduct any type of statistical analyses like we've done here or that we're talked about all semester long. So you can't calculate an average on words. So in other words, if a person says, I went to the store, how do you calculate an average for I went to the store? So what is that in reference to? So one of the first things that you would have to do is have to convert that narrative form into numbers by saying, okay, well, did they do an activity that's outside of the home? And I went to the store, yes, that counts as a value of a 1 because they went to the store, they did an activity outside the home. So here you have to specify or set some type of criteria to make that conversion to numerical form. So again, very important, we're comparing our participants on some number. And in our particular case, we're comparing them on their exam performance. So whatever score it is that they get out of 10. Now remember, one of the first things that we're thinking about here is that we're not thinking about the individual. We're thinking about the group's performance. So if you've noticed in terms of the example that I've set up for you, that I've talked about smokers and non-smokers, I haven't said Alex who's a smoker, Ashley who's a non-smoker, Kelly, who's a smoker, Bert, who's a non-smoker. I haven't said any of those things, but rather I'm just saying the group as smokers, the group as non-smokers. So here, individuals are going to make up the group, so everyone's individual exam score is going to make up the average for the smokers and the average for the non-smokers. So we do have to consider that. And that we're also going to have a standard deviation for the smokers and a standard deviation for the non-smokers. So in other words, we'll have an average for smokers, non-smokers on exam scores, and we'll also have a standard deviation for one group and for the other group. So we're going to have two averages and two standard deviations, which is going to be very, very important for us when we look at the statistical formula associated with T. So if we look at other core assumptions associated with T, there are really three primary core assumptions that we have to look at. The very first one is in regards to our dependent variable. So we've already talked about it having to be numerical in its nature. So it has to be quantitative in its form. So when we're looking at our dependent variable, our outcome, or what we call our criterion, our influenced, or our dependent variable, we have to make sure that it is, number one, quantitative in its nature. We would really like for it to be interval or ratio data. So in other words, it doesn't necessarily have to have a true zero form or a true zero representation in terms of the data. But if it doesn't, or if it does, that's okay. That's the kind of data that we're wanting to work with. So it doesn't really matter if it has a true zero or not. But as long as we have differences in terms of our values that actually correspond to differences in terms of quantitative differences, that's really what we're looking for. So remember what the criteria for having an interval on a ratio scale, that's really what we want. If we have nominal or even ordinal data, in certain instances you might be able to do inferential t-stat test on it, but to be honest with you, it's best if we do interval or ratio scale. This is really the standard that we use. We really don't want to use ordinal or interval data, or sorry, ordinal or nominal data in those particular cases. Our second requirement for the dependent variable is that the outcome has to be normally distributed. So in other words, when we look at the group's performance for smokers, we would expect that just for smokers, their distribution of scores would be normally distributed. So in other words, remember when we talked about looking at the histogram and we talked about frequency distributions, that we talked about having a normal distribution. So that was one of the key requirements that we now have here for using our t-test, is that we have to have a normal distribution of scores for each group. So here I'll write for each group. So in other words, for group 1 or for my smokers group, their scores have to be normally distributed. So again, they have to meet those proportionality requirements of 50-50, the 1, 2, and 3 standard deviations above the mean in those specific percentages. So remember the 34.13%, the 14 point some odd percent, and the 2.28%. 1, 2, and 3 standard deviations above and below the mean. That's what we're looking for in terms of a normal distribution. If we don't have a normal distribution, is that going to be problematic for us? The answer is yes and no. The answer is yes, because the more non-normal that scores become in terms of the group, so the more kurtotic the distribution becomes, the less accurate your statistical test may become. But even in the cases where we don't have a normal distribution, it's typically okay. I mean, you can still do your statistical test and it really shouldn't be too big of a problem, to be honest with you. Our second key assumption or requirement that we have to have for our t-test is that we have to have equal variances of scores across groups. We also call this the homogeneity of variance assumption, and essentially what the assumption of homogeneity of variance suggests is the following. The variability between the scores of both groups should be equal. So in other words, if I look at the variance or the standard deviation, for instance, of group 1 versus that of group 2, we should have similar spread of our scores. And I know that sounds like a very weird thing to think about, but let's think about it in this capacity. So let me just draw this out for you. Sorry, guys. There we go. Okay, so let's assume here that we have the smoker group. So these are my smokers. And then over here, I have my non-smokers. Okay? So here, what the homogeneity of assumption is asking for is it's saying the following. When you calculate variance, So if you all remember when we talked about variance earlier in the semester, when we calculated variance, one of the key things about variance or even standard deviation, because remember both variance and standard deviation are very similar to each other. One of them is just the squared scores and the other one is the non-squared scores that we're dealing with. But essentially variance and standard deviation talked about the spread of the scores. So the spread of scores. There we go. So our spread of our scores. So what does that mean? It means the amount of dispersion that we have. So imagine grabbing, a bunch of coins in your hand, right? So you have about 10 coins, and each coin represents a participant. If you were just to drop them on the floor, all the coins would kind of spread out, right? The more spread out that those coins are, it means the more dispersion, the more variability there is within that data set that you just dropped on the floor. Okay, that's what that would mean. So again, if you have 10 coins in your hand, let's assume that each one of those coins represents one participant. If you throw them on the floor and they spread out, the amount that they spread out from the center of the group's performance, so again, the mean, that ultimately is going to be the spread of our score. So the average of the spread of our scores. So here, one of the things that we want to do is we want to think of the following. What does variance and standard deviation really do for us? Well, it tells me the spread of my scores, but if we look at standard deviation is ultimately telling me how far on average are my scores deviating from some central point, so from the mean, right? And one of the things when we talked about standard deviation is I talked about what do you want? Do you want a lot of spread or do you want a little bit of spread? So what is this idea of the spread of our scores? The spread of our scores ultimately is going to indicate for us some aspects associated with like individual differences if you want to think about them. So here we have to think about it in this capacity. So if smokers are receiving or smokers are smoking in this particular case, and we're giving them an exam, we would expect that all smokers in an ideal world would all perform identical to each other. Because remember, that was one of the things that I wanted for standard deviation and for variance. I want it to be as close to zero as possible. Why? Because the closer that my scores are to zero in terms of variance and standard deviation, that's ultimately indicative to me that everyone's performing very similar to each other within the group. So in other words, group one, my smokers, we need to calculate a standard deviation for them, or we also need to calculate variance, right? And we will calculate variance along the way because remember, variance is the precursor to standard deviation. We also need to calculate a standard deviation and variance for my non-smoking group. Now, if you're asking yourself, well, why don't you just calculate one standard deviation and one variance, including everyone's data? Well, that's not fair. It's like me calculating an average for you if you took an exam in statistics, but then also then somebody else took an exam in physics, and now I'm using both of your scores to come up with the average of performance. It's not fair. So it's not fair for me to have these two different groups and then use one single value that represents both groups because they're different. So here my smokers are different than my non-smokers. So here I have to calculate an average for my smokers. I have to calculate standard deviation and a variance for them. I have to do the same for the non-smokers. I have to calculate an average, standard deviation, and a variance for them as well. So ultimately, one of the things that we want is we want our spread of our scores to be as low as possible. Because the lower that my spread of my scores are, it means the more similar my participants are actually participating. So if we give smokers an exam and all smokers are being treated the same, and the only thing that they have here in common is that they're smokers, we would expect then that everyone's scores would be very similar to each other. So here I'm going to try to draw as many dots as I can that are close to each other, okay? So in other words, I want people to participate as similar to each other, as close to the mean, so close, all right, yep, there we go, so close to the mean, okay? Why? Because the closer they are to the mean, that means the more similar they are. That's a good thing for us. Why is it that that's a good thing for us? Because then this would indicate for us that they are a good reflection from the population. So in other words, they are a pretty good representation of the population that we randomly sampled them from. So in other words, out there in the real world, there are people who are smokers. I've randomly sampled from them, and I'm hoping that the people that I get to represent my smokers should all participate the same. But let's say, for instance, there's someone who scores over here. So everyone's scoring around here, and one person scores over here. This person more than likely is going to be our outlier, because remember we've talked about outliers before. And why are they going to be my outlier? Because probably they're going to come from another population. So in other words, the person who scores really well, they might have scored really well, and they may only smoke 1 cigarette a month. Are they really going to be considered to be a smoker? Probably not, especially if all these people here are chain smokers and they smoke 10 to 15 cigarettes a day. So here, this one person may not be reflective of that of this group's performance. So we want to make sure that we cut out any outliers, or we deal with them appropriately and we put them in the right groups, because for instance this person might actually correspond to the non-smoking group, and we want to make sure that within our scores themselves for the smokers they're all very similar to each other. So we want variability to be very small. The same thing over here for non-smokers. Okay, I want my non-smoker scores, whoops, there we go, to all be very, very similar to each other. I don't want them to be far away from each other. Why don't I want their scores to be far away from each other? Because again, the further away that their scores are within the group, it means that the more different everybody is. So in other words, they're acting differently because of different individual factors that are making them respond differently on my dependent variable. So I want them to be as close as possible in terms of their standard deviation and variance, in terms of their spread of their scores. So now what the homogeneity of variance assumption is testing is it's ultimately saying the following. When we compare the variability within the group of smokers and the variability within the group of non-smokers, there should be no significant difference. So no significant, there we go, difference. Why? Because if for one group we have a lot of spread, and then for another group we have very little spread, that means that within one group they're acting very differently, and in the other group they're acting very similar to each other. So the group that is acting very, very differently, that they have a lot of spread of their scores, potentially then the effect that they display, their score on the exam as an average, is probably not going to be representative of their group's performance. It's probably going to be representative of a couple of different values that are really pulling the mean in that direction. So here, if everyone's performing very similar to each other, it's more reflective of the group's performance because everyone's performing very similarly. But if we have a lot of spread in our scores, then that would mean that people are all over the place and the average is not really going to be representative of that group's performance. So here, what the homogeneity of assumption predicts is that there is no significant difference between the variabilities between the groups. So within one group, we should have whatever standard deviation it is that we have. So let's say, for instance, we calculate variance and standard deviation, and we find that variance for group smokers is a 2. And here I'm just making up these numbers. For standard deviation, we find a value of a 1. Over here, we would expect then that the non-smoking group should have a variance that is very similar to that of the first group. Now, is it going to be exactly the same? No, probably not. But let's assume here it's a 2.1 or a 2.2 or a 1.9. Very, very similar. And then our standard deviations would also be very, very similar to each other. That's what the homogeneity of variance assumption is predicting here, that the groups are not significantly differing in terms of the amount of variability that they display within each other and then compare to each other. So in other words, when we compare the variabilities between the two groups, there should be no extreme differences in terms of how much variability they display within the groups. So here, if for one group we have a standard deviation or a variance, let's say a variance of a 6, and then for our other group, we had a variance equal to a 2. That's a lot of difference between those two numbers. So potentially, this group here has a lot more variability than this group here. So potentially, the results may not be accurate in terms of the representation for the group that has a lot of spread. Okay, that's ultimately what it means for us. So here we want to make sure that we have as close the variability as we can between the groups. That's very, very important. So within the group, it doesn't really matter if the variability is little or a lot within the group, but between the groups, there should be very little difference. That's what we're looking for. Assumption number 3, we should have independent observations for both between and within groups. Very, very important. So in other words, if I'm comparing individuals, so the smokers versus the non-smokers, we should really try to keep the smokers and the non-smokers as separate from each other as possible, so that way they don't influence each other. So in other words, when I'm testing the smokers, the non-smokers really shouldn't be in the room or come close in contact to the smokers, because the smokers may affect the non-smokers, or the non-smokers may affect the smokers. Who knows? Also, within the groups, making sure that everyone has their own independent observation. In other words, this is not a team effort. This is not a group assignment. When you're collecting data, you want to make sure that everyone is giving you their own particular data. So the people who are in the smoking group are doing only their task individually. So in other words, they're not copying from each other. They're not working as a team, because then the scores really wouldn't be independent for within the group itself. So you want to make sure that you want to have the observations between the groups and then also within the group to be independent. That's very, very important for us. All right, so now let's take a quick look at the formula for independent samples t-test. This is our formula. Now, if you're looking at this formula and you're already telling yourself, no way, I am totally not doing it. So if you're just saying to yourself, nope, totally not going to do this, I quit, I'm going to go ahead and pause the lecture, I'm done, I'll drop the class, I don't know, something, don't. Because one of the things that I am going to do for you guys is, it would be very, very unfair for me to ask you guys to calculate this equation on an exam, because it would take so long to actually do. It's a very, very lengthy process. I'm going to work through an example using this formula, but it's more important for me for you to understand the conceptual issue associated with the formula. So what's the purpose of using this formula? And then also focus in on the interpretation. Because again, out there in the real world, guys, I'm going to be honest with you, no one's really going to come up to you and tell you, hey, what's the formula for the independent samples t-test? And if they do, I promise you guys can call me and you can be like, dude, I don't know what you taught us, but you needed to have taught us exactly to memorize this specific formula. And that's not the case, guys, to be honest with you. No one's ever going to do that. We use statistical programs to do these analyses for us because it's such a lengthy process. I'm going to work through one example here, and you're going to notice it's going to take some time to actually work through this example, which you guys are always more than free to try it out. So if you ever have raw data lying around anywhere, and you want to compare two groups that are mutually exclusive from each other, and you're measuring them on the same thing, go for it. Do the formula, see if it comes out to what the computer actually tells you. So what SPSS is going to tell you in terms of the statistical program. So here's a very, very lengthy formula. So conceptually, this is what I need you to know about the T formula. In the numerator, you'll notice that we have the average of group 1 and the average of group 2. Now you'll notice here, are there any population parameters given to us? So is mu presented? The answer is no. Is capital N presented? The answer is no. Is sigma present? And the answer is no. Why? Because this is an independent samples t-test. There is no t-test for the population, to be honest with you. There is no t-test that we would say, hey, we're going to use our population parameters. So in reality, you're going to use this formula. This is always the formula that you're going to use. Now, this formula comes in many different forms, so different textbooks are going to use different formulas, but they all come out to being the exact same thing. So for instance, one of the formulas that I've seen in the past, what's here in our brackets, for instance, I've seen them do 1 divided by our sample size plus 1 divided by sample size, and it essentially comes out to being exactly the same thing here. So don't worry about different formulas being presented to you, because they both really conceptually mean the exact same thing here. So conceptually speaking, what I want you to look at is I want you to look at first the numerator, right? Because that's the very first thing that we want to look at, and it looks like the simplest thing. Here, essentially what my numerator is saying is the difference between group 1 and group 2. That's what we're looking at here. In our numerator, this is what we've been calling all semester long effect variance. That's what we've been talking about all semester long. The differences between my groups that are due to my manipulation or my control. What's the best estimate that I have of my manipulation or my control? It's my group's performance. That's my average. That's what I assume is due to my manipulation or my control. So if the groups differ, I'm assuming that they're going to differ because of me. not because of other extraneous factors that exist out there, but I still have to consider those extraneous factors. So in my denominator, what do I have? In my numerator, I have effect variance. In my denominator, if you guessed it, we have error variance. And that's what I told you was the conceptual formula for all inferential statistics that we're going to be dealing with for the remainder of the semester. Effect variance divided by error variance. Now, one of the things that you'll find is that effect variance and error variance are calculated very differently for different statistical formulas. Be very cautious about that, but as I introduce more statistical formulas as the semester continues to go through, I will always point out what is effect and what is error. The numerator is always effect, the denominator is always error in our particular cases. So very, very important for us. So again, effect variance, in this particular case, the differences between my two groups. Error variance, it's all this formula down here. Now I told you earlier on in the semester that variance would come up in other instances. This is one of those instances that variance comes up. So there's variance represented in my formula. Not standard deviation, it's variance, because remember it's got the square. And then let's work through the other pieces of the formula, because here it looks a little bit intimidating, but don't really get too worried about it. One of the great things about this formula is that it labels very, very well for you what corresponds to what group. So remember, I told you that we need to calculate an average for group 1, smokers, group 2, non-smokers. So here in my formula, we always have subscripts in terms of all our values that are represented, or our symbolic notations that are given to us. So for instance, this is the average of group 1, average of group 2. So we're going to say average of smokers, average of non-smokers. Here you'll notice now we have lowercase n. Remember that lowercase n represents your sample size, not your population size, because remember, again, we're not dealing with the population, we're dealing with the sample. So lowercase n represents the sample size for group 1. Because remember, in certain instances, you may get more people to participate in one group versus another group. And that's very, very important. That in one group, you may have 30 participants. And in another group, you may only have 29 participants. So ultimately here, you may have differences in terms of your sample sizes. So it's important to know how many people are in each one of your groups. So we have here the sample size for group 1 minus the value of 1. Multiplying that times the variance for group 1, because again you see that value of a 1 right there, so that subscript of a 1. So that's the variance for group 1. So I do need to calculate the variance for group 1 and for group 2. Sample size for group 2, variance for group 2. In the denominator of this equation here that we have for the denominator of the denominator, if you want to think about that, we have sample size for group 1 plus sample size for group 2 minus 2. This is what we're going to label here, in our particular case, degrees of freedom. Okay? Degrees of freedom should sound like something that you know, because we talked about it when we talked about calculating standard deviation for the sample, that we would use n minus 1 in our denominator for our formula. So remember, for our formula, it was the sum of my squared deviations. Here, let my pen catch up to what it is that I'm saying here. There we go. Divided by n minus 1. So that's the formula here for variance. And then we would take the square root of that formula and they would give a standard deviation. So again, we always talked about n minus 1, referring here to our degrees of freedom. Now here, you're probably asking yourself, well, why is it that we take then minus 2? Why didn't we say n minus 1? Because remember, how many groups am I dealing with? I'm dealing with 2 groups. And remember, I've been telling you up to this point, we need 2 averages, as we have here, 2 variances, because I need the variance for group 1 and the variance for group 2. So in other words, when we did the calculation for variance for group 1, since it is a sample, we took n minus 1 for group 1. So for the smokers, we took n minus 1. For the non-smokers, we also took n minus 1. So in other words, essentially what the denominator of this portion of the formula is telling you to do is it's telling you, look, you're going to take n minus 1 for smokers, n minus 1 for non-smokers. So let's assume here that for the smokers, you had a sample size equal to 20. For non-smokers, let's say your average was your number of participants was 21. So we have 21 people. So 20 for smokers, 21 for non-smokers. If we take n minus 1 for smokers, that will leave me with a value of a 19. For non-smokers, it'll leave me with a value of a 20. Right? So n minus 1 for smokers would be 20 minus 1, giving me 19. For non-smokers, n minus 1, 21 minus 1 equals 20. So in this particular case, that would give me degrees of freedom equal to 39. Right? Now, if we do this portion here, just as it's given to us, if we say 20 plus 21, which should give us 41, right? So that's 41, minus 2, as we have here, leaves me with the value of 39. So if you'll notice, in both cases, doing the formula in different ways doesn't really matter how you do it. So doing it like this, n1 plus n2 minus 2 gives me 39. N minus 1 for group 1 gives me 19. N minus 1 for group 2 gives me 20, giving me degrees of freedom of 39. Or you can also do the following, n total, here I'll just write total very quickly, n total minus 2, which is essentially adding these two numbers up. So 20 plus 21 gives me 41, minus 2 gives me 39. So ultimately here, why is it doing this? Why is it taking 2? Because it's taking n minus 1 for group 1 and n minus 1 for group 2. Always keep this in mind for t-test, that for t-test, degrees of freedom are always n total minus 2, or n for group 1 minus 1 plus n for group 2 minus 1, giving you, in this particular instance, degrees of freedom minus 2. All right, so let's go ahead and try out an example. So with our example, again, we are comparing smokers versus non-smokers. And again, the research question that we had is the following. So I have a research question and then I also have a research prediction. My research question was, does smoking significantly affect exam performance? So in other words, by somebody smoking or not smoking, can that potentially affect, improve, or worsen an individual's exam performance? So why would this kind of question be important for us? Well, let's just say, for example, a campus is or a campus has a non-smoking policy, right? So if an individual wants to smoke a cigarette and they have to go off campus to go smoke a cigarette right before their exam begins, so they go smoke a cigarette off campus and now they have to run to campus to take the exam, they already come with multiple anxieties. So they're already coming with the anxiety of potentially having their addiction, the anxiety of having to make it on time to the exam, now the anxiety of the exam itself. So there's lots of anxiety that's being built up. So here, ultimately, if we compare our smokers to our non-smokers, we find the following scores in terms of their exam. Now remember that their exam is out of 10 points. So here we have participant 1, 2, 3, 4, and 5 for the smokers and then for the non-smokers. So we have 10 total participants. Why do we have 10 total participants? Because we have 5 coming from the smoking group and then we have 5 who are coming from the non-smoking group. So our sample size is equal in this particular case to 10. Okay, so these are going to be our values that we have in terms of the data that we've collected for our pseudo experiment. So what we're going to want to do now is we're going to want to calculate using the formula that we have on the previous screens. We're going to use that formula to be able to actually calculate to see if we have a significant difference between smokers and non-smokers. So let's go ahead and begin doing that. All right, and there we go. Okay. So again, remember that we have our following values. Our values are a value of 3, 2, 5, 4, and 5. And again, just to double check, I want to make sure that I have them for the right groups. So this is for my smoking group. And then for my non-smokers group, so these are smokers. And then for my non-smokers, I have values of 7, 6, 8, 8, and 9. And these are going to be for my non-smokers. Okay, so the very first thing that we want to make sure that we do is we always want to know our sample size. So remember, we have sample size of 5 for my smokers, sample size of 5 for my non-smokers. So we have an N total equaling to 10. Okay, so I have 10 total participants in this particular case. So now one of the things that I have to do in terms of my formula is I have to calculate my average, because remember, in terms of my formula for T, we begin with our numerator that's the average for group 1 minus the average of group 2. And here we're going to label our smokers group 1 and our non-smokers group 2. Okay? So that's the first thing that we want to do. We want to calculate my average. So in our specific case, the sum of X for this particular group, for our smokers group, is going to be a value of a 19. We're going to divide that by 5, and that's going to give me an average equal to a 3.8. For my non-smokers group, I have the sum of X equaling a value of 38, and we're going to divide that by a value of a 5, because again, that's my sample size, and that's going to give me an average equal to a 7.6. So if I do the quick math looking at the difference between my averages, so again, this is going to be the numerator of my T statistic, I'm going to have 3.8 minus 7.6. Now, in our case, 3.8 minus 7.6 is going to give me a value that is negative 3.8, and it's okay if you have negative or positive values here. Doesn't really matter if we have negative or positive values, because one of the things that we're going to look at with our sampling distribution, and again, that is a key word there, right, our sampling distribution. When we look at our sampling distribution, you're going to notice that we have, again, a normal distribution. So we have positive and negative values in terms of my T statistic. So we're going to be able to look at those values on that distribution. So again, that's my numerator. And then in terms of my denominator, again, I just want to take a quick look at that. Remember that we have our sample size for group 1 minus a value of a 1. Multiply that times my variance for group 1. Oops. Here we go. Plus sample size for group 2 minus 1 times variance for group 2. And we're going to divide that whole formula, or that denominator, by N1 plus N2. So the sample size of group 1 plus the sample size of group 2 minus 2. And we're going to multiply all of that times the sample size of group 1 plus the sample size of group 2 divided by the sample size of group 1 times the sample size of group 2. So here we're going to add them, and here we're going to multiply them. Okay? So we already know a lot of the information that's here in my equation. The big mysteries that we have here are variance. Those are the big mysteries that we have. So we already know what sample size is for group 1, for group 2. We already know what sample size total is as well. So we already know a lot of the missing information that's in my equation. I already now know what my averages are as well, because I've already calculated those values there. I already know what the difference between those values is. So I already know what the denominator is going to look like in terms of my, or the numerator is going to look like in terms of my formula. But the key here that we need to do is we actually need to calculate my variance. And we're going to go ahead and calculate standard deviation just along the way, since it's just one extra little step for us. Now remember, we are dealing with the sample. So with the sample, we're going to be using the following formula. So the sum of our squared deviations, divide that by n minus 1, and we're going to take the square root. So remember, when we take the square root, this is going to be my standard deviation formula. My variance formula is the same thing, except that we are not taking the square root of this equation. So here we're going to divide by n minus 1, but we're not taking the square root. So that's what's going to make the difference between the two. So let's go ahead and, again, using the data that we already have in terms of our example, let's go ahead and, again, for our smokers, whoops, there we go. We have the data that is 3, 2, 5, 4, and 5. And again, I already know what my average is. My average was a value of a 3.8. So remember, in terms of my equation for standard deviation, I want to take each score that I have in my data set for that specific group, and I want to subtract the average from it. So 3 minus 3.8, 2 minus 3.8, 5 minus 3.8, 4 minus 3.8, and 5 minus 3.8. So here I want to look at what we are going to call our deviations. So my deviations are going to equal, in this particular case, to negative 0.8, negative 1.8, positive 1.2, 0.2 positive, and last 1.2 positive. Okay, so this is going to be for, again, for my smoking group. Now remember, one of the first things that we have to think about in terms of calculation of standard deviation and variance is that we need to make sure that we square our values or our deviations. And the reason that we're going to square our deviations, remember, is that we want to eliminate that zero value that we may potentially get if we just leave all our values with positives and negatives. So we want to make sure that we're going to square each one of these. So I'm going to go ahead and do that. So we want to square each one of them. So when we square each one of our values, we should get the following. For our first value, we get positive 0.64, positive 3.4, or 3.24, 1.44, 0.04, and last 1.44. So now we're going to take the sum of these values, and when we take the sum of those values, that should give me, for my numerator, so again, the sum of my squared deviations is going to be equal to a value of 6.8 for my smokers. So 6.8, now divide that by 4. Why are we dividing by 4? Because remember, our sample size was equal to a 5. My denominator requested that we have n minus 1, or what we call degrees of freedom. So I took 5 minus 1 to give me a value of a 4. So thus 6.8 divided by 4 should give me a variance equal to a 1.7 and a standard deviation equal to a 1.3. Okay, so now I've already solved for group 1, because remember, this is a representation of group 1. Oops, there we go. I already now know what variance is equal to. So here in the formula, I now know what variance is going to be equal for in the denominator of my t-statistic formula for group 1. Okay, now I need to do the same for group 2. Okay, so now we're going to have our non-smoking group, so non-smokers. And again, my values here were a value of a 7, 6, 8, 8, and 9. Remember that my average was a 7.6, so we're going to calculate our deviations. So all our deviations are going to equal out to negative 0.6, negative 1.6, 0.4 positive, 0.4 positive, and last 1.4. Okay, perfect. And that's a positive value. So again, remember, now we're going to square our values. So as you guys can see, this is a very lengthy process just to get to our t-statistic. So I'm going to square all my values. So once I square my values, this should be equal to 0.36, 2.56, 0.16, 0.16, and last 1.96. We're going to have the sum of those values. So in this case, the sum of my squared scores in this particular case is going to equal to a value of 5.2. We're going to divide that again by 4 because remember, my sample size was equal to a value of a 5. Again, my denominator requested n minus 1, so my degrees of freedom equaling 5 minus 1 equaling a value of a 4. So 5.2 divided by 4 is going to equal a value for variance of 1.3 and for standard deviation a 1.14, sorry. So now here, our formula does not request us to have standard deviation, but I've gone ahead and calculated standard deviation just in case I need it in terms of like reporting any statistics or anything that I may need for the future. Okay, so now I know my variance for group 2, because remember this is for my non-smoking group, so group 2. I know my variance for group 1, and now we're going to continue on with our formula. We're going to plug in where we left off. Okay, so I'm going to go ahead and just have it on another page. So again, we already knew that the difference between the two averages was a negative 3.8 because we looked at the difference between 3.8 and 7.6, giving me a negative 3.8. So again, with our formula, and I'm just going to draw it down here, we have n1, so again, that's a value of a 5, so our formula was n1 minus 1 times our variance for group 1 plus n2 minus 1 times the variance of group 2, divide that by n1 plus n2 minus 2, and we're going to multiply all of that by sample size of group 1 plus the sample size of group 2, divide that by the product of sample size 1 times sample size 2, and we're going to take the square root of this entire formula for the denominator. Okay, so I know what my sample size was, right, for group 1, which is a value of a 5. So let me just do that a little bit further up over here. So 5 minus 1 times, and again remember, my variance for group 1 was equal to a value of 1.7 plus 5 minus 1 times the variance of group 2, which is a 1.3, divide that by 5 plus 5 minus 2, because remember sample size for group 1 was a 5, sample size for group 2 was a 5, minus 2, times 5 plus 5, because remember sample size for group 1 plus sample size for group 2, divided by 5 times 5. Because we have the product term here of our sample sizes. So now the next step is really just for us to do all the math in this particular case. So 5 minus 1 is going to be equal to a value of a 4 times 1.7 plus 4 times 1.3. Divide that by a value of an 8, because 5 plus 5 is 10 minus 2 is going to be in this case 8 times, which would be 5 plus 5 is equal to 10 divided by 25, and 10 divided by 25 should give me a value equal to 0.4 if I'm not mistaken. So now that we know what this portion of my formula is equal to, we're going to just now continue on to work with our formula in this case. So 4 times 1.7, and again if you're following along doing the math, 4 times 1.7 is going to equal a value of 6.8 plus 4 times 1.3 should give us a value of 5.2. And if you add those two numbers up, that should give you a value of a 12. And we're going to divide 12 by 8, because again, 8 was that portion of the denominator for that fraction in that instance. So 12 divided by 8 will give you now a value equal to 1.5. So now 1.5 times 0.4 will now give you a value equal to 0.6. Now remember, you still need to do your square root because we still have that portion of our denominator. So we need to now take the square root of 0.6, and that will give us a value of 0.77. So in other words, this is our estimate for error variance for our t statistic. So now you notice that we have negative 3.8, divide that by 0.77 as my t-value formula. So 3.8 divide that by 0.77 is now going to give me a value of negative 4.93 or 94. We'll round off here to the second decimal point. Now remember, it's negative because I had a negative numerator in that case. So again, remember to always include your negative in this portion. Okay, great. So now you have a t-value that is equal to negative 4.94. The big question is now, so what? What do I do with this? This is now where we come across a very old friend of ours, and I really shouldn't say old friend of ours because this is a relatively new thing that we just introduced. But after we calculate our statistic, now we want to test our statistic for significance using, of course, null hypothesis significance testing. So just like I mentioned earlier on in other lectures, we are going to now be doing null hypothesis significance testing pretty much for the remainder of the semester. So now what we want to do with null hypothesis significance testing in our particular case is we now want to test our statistic that we calculated of t negative 4.94, and we want to see if this value here is significantly different from the zero predicted by the null hypothesis. Because remember, that was part of what I talked about earlier on in the lecture. So if we go back to some of the introductory topics that we discussed associated with the t-statistic, is that I mentioned to you that the null hypothesis predicts that mu1 is equal to mu2, which is equal to 0, or mu1 minus mu2 is equal to 0. And in our particular case, we found that our group averages for smokers and non-smokers were not equal to each other, and the difference was not equal to 0. But now I want to know, is my t-statistic then significantly different from the t-statistic that is predicted by the null hypothesis? Because remember, in my formula for t, what went in my numerator? The average of group 1 minus the average of group 2. If we replace those averages, those sample averages, with population parameters, so mu1 minus mu2, you'll notice now that that fits into here, into the way that we symbolically stated the null hypothesis. If we would have actually found that there were no group differences between smokers and non-smokers on their exam performance, we would have expected then that this difference between the two in terms of the formula that we were using would be equal to 0. So thus, the numerator would be 0 divided by any number, and it would have been equal to 0, right? So 0 divided by anything is 0. So that's why the null hypothesis predicts that the difference between the two groups is going to be equal to 0. So here, that's what the null hypothesis predicts. Or if we look at the formula, t would be equal to 0. Okay, that's what it would predict. But the alternative hypothesis predicts that t would not be equal to 0. So in our case, we find a statistic that is t equal to negative 4.90. So 4.90. And now what we want to do is we want to test my statistic versus the 0 value given to me by the null hypothesis. So again, we have to now revisit this idea of null hypothesis significance testing in our 4 steps. Step number 1, again, state the known alternative in terms of population parameters. Number 2, we're going to collect the data and calculate the inferential statistic. We've already done that, right? We've already gone ahead and done that here for ourselves. The next step now is to test our statistic for significance. So again, here, what we now want to do is we want to make sure that we identify if my statistic falls in the region of rejection or not. If my statistic does land in the region of rejection, I get to reject the null hypothesis and suggest that here the groups do significantly differ in terms of their exam performance. Or if my statistic does not land in the region of rejection, I'm going to retain the null hypothesis and suggest that there is no significant difference between the two groups. I'm also going to select my alpha level, making sure that I select my alpha level at 0.05 or whatever the case may be. And I also want to make sure that I attain my specific regions of rejection with the 1 versus 2 tail testing as well. So making sure, am I going to look only at one portion of the distribution or on both sides of the distribution? And then the fourth part of null hypothesis significance testing, drawing our conclusions regarding the null and my prediction. So in other words, am I going to retain the null hypothesis or reject the null hypothesis? And then I still have to evaluate my research hypothesis. So here I still have to look at my research hypothesis and say, was I right in terms of my prediction that I made at the beginning of the study? So I predicted that the groups would differ, that the smokers would have lower scores than the non-smokers, significantly lower scores. So now here I really want to test that idea. So what do we need to do? I need to find my critical value. Now for a t-test, the use of the critical value is going to be very, very important for us to identify our critical regions or our regions of rejection. Now, for our critical value, we have this sheet. You'll find something very similar in terms of the back of your textbook, but I'll post this up also on Blackboard for you, just in case it is that you want to take a look at it or that you're going to use it. So for instance, on the exam that's coming up for the final, this would be a very useful table for you to know how to interpret and how to find critical values. So here we're going to have our critical value sheet. And here what we want to do, just as we did with our unit normal table, is we want to find the boundary of where my region of rejection begins. Okay, so in other words, I want to find my critical value so that way I know where to look on my distribution to see where my region of rejection is going to begin. Now, what is my distribution going to look like for my t distribution? My t distribution is essentially going to look like a normal distribution, where the mean of that distribution is equal to 0. So now what I want to do is I want to know here where is my region of rejection. Okay, how am I going to do that? I need to use this critical value table to identify where my region of rejection begins, so that way I can determine if my statistic landed in there. Okay, so how are we going to find our critical value using this sheet that I've just shown you? Well, the first thing that we're going to do is we need to use the degrees of freedom column. Now you'll notice here that we have that column labeled right here. So there's my degrees of freedom column. My degrees of freedom column essentially, again, is calculated using n total minus 2, or n for group 1 plus n for group 2 minus 2. So in our particular case, we already knew that we had 5 individuals for group 1, 5 individuals for group 2, or 10 individuals, minus 2, because remember, why are we taking minus 2? Because we have group 1 smokers and group 2 non-smokers. So we do n minus 1 for group 1, n minus 1 for group 2, leaving me with degrees of freedom equaling an 8. So here, I'm going to look at this section right here. So that row right there. Why am I going to look at that row? Because it corresponds to the degrees of freedom associated with my specific sample size. So in other words, I had 10 individuals participate in my study. I want to look at that specific column that we have there. Okay. So in our particular case, now we also need to identify our alpha level. Now, if you remember from previous lectures, we talked about what the maximum value for alpha level is. And we said that the maximum value for alpha level is 5% or 0.05. Okay. Now here, we can always set it lower, but we never want to go higher than 5%. Now we also need to know, are we going to look at one tail or are we going to look at both tails of my distribution? Remember, with our two-tailed distribution, if we're going to look at both sides, here that's more of a conservative statistical test because here I have the safety net just in case my stat goes in the opposite direction. With the one-tail test, it's much more riskier because you don't know in what direction your statistic is going to go. Okay, so here we're setting our alpha level, the probability of committing a type 1 error, right? So here we're setting it at 5%. And now we're deciding, well, are we going to have one or two tails that we're going to look at? Okay, that's ultimately the conclusions that we're trying to draw. So in our particular case, and again, since you see the distribution here that I've drawn for you, that it is normal, we do have a positive and we have a negative side of the distribution. So you get to decide. Remember that all of this, the selection of one versus two tails, alpha level, this is all done a priori. So in other words, it's done before the fact. So before I even know what my statistic value is, before I even calculate that value, I've already selected what my alpha level should be, and I've already also selected if I'm going to do a one or a two-tailed test. I've already done that. Okay? I never do this after the fact. And especially since we do this using computers, computers always set these things, these conditions prior to us ever doing our statistical analysis. Okay, so now you'll notice in terms of this sheet here that we have, you'll notice that they're very important terms that we have here. And here I'll just quickly remove that so we can continue on with looking at this aspect. So here you'll notice that it says one-tailed or two-tailed. So there's this issue of one versus two-tailed. I want to play it safe and I want to do a two-tailed distribution. Okay, because I don't want to be too risky. And I want to set my alpha level up at the maximum, at 5% or at 0.05, because I want to make sure that I have power. I want to have the maximum power that I can associated with alpha level. I don't have too much power because of my two-tailed, because remember here, since I have a two-tailed, I have to split my 5% between the two tails. So I now have 2.5%, so 0.025, or 2.5% on each side of the distribution, so on the right and also on the left. Okay, so I want to look at the one that says level of significance two-tailed test, because that's what I want. I want the two-tailed, okay, because I want to play it safe. So now you'll notice that we have all the different alpha levels. So these represent alpha levels. All these values that are right here underneath where it says level of significance. So we have 10%, 5%, 0.02%, 0.01%, 0.001%. Now here, what we're going to do is we're going to look under the column that we've stipulated for our maximum. So I said that my maximum alpha level was 5%. So I'm going to look under the 5% column. Okay, so I want to look at 5% column, two-tail test, and I want to look now at the row associated with 8 degrees of freedom. So now you'll notice here that my critical value is a value of 2.31. Now remember, since it's a two-tailed test, I need positive 2.31 and negative 2.31. Why? Because I have on each side of the distribution positive and negative. So remember that I have a positive side and I have a negative side. So on this side, my critical region starts at 2.31 positive. Over here, my critical region starts at negative 2.31. How did I find that 2.31? I went to where it says level of significance for a two-tailed test because I've decided it's a two-tailed test. I had 8 degrees of freedom, again, n total minus 2. And I looked at the 0.05 or 5% column associated with level of significance two-tailed test. Now you'll notice here that if you look at the top where it says 0.025, technically here you could look on here and say, okay, well, one of my tails has 2.5%, my other one also has 2.5%, and it would still give you the same value. But don't make the mistake of looking on this column, or sorry, under this specific row, because that level of significance is going to refer to 5% for one tail, 5% for the other tail, because this is a one-tailed test. And I don't want a one-tailed test, I want a two-tailed test that has the maximum alpha level at 5%. So here it assumes that it's 2.5% per tail, okay? That's what it's already doing in that particular case. Okay, so now what I want to do is I want to test my statistic for significance. And here, before we continue on, let me just add a new page very quickly here. That's not what I want to do. Okay. All right, so we're going to go ahead and add in a new page. So now again, remember that in our specific situation, we have, move that away, my distribution looks like the following. So now that we know what our critical value is based on our critical value sheet, again, remember our critical value is a positive and a negative 2.31. And we also know what our statistic is that we had calculated from our example, which was a t negative 4.94 that we had calculated from our data comparing smokers versus non-smokers. We'll now here create our regions of rejection, so at a positive 2.31 and also at a negative 2.31. Because remember, we had positive and a negative side of the distribution. Since we were looking at both sides of the distribution, we decided that we were going to do a two-tailed test rather than a one-tailed test. So continuing on looking at this particular issue of where my statistic falls, so based on a two-tailed distribution, so two-tailed, with the sample size equaling 10, degrees of freedom equaling 8, and an alpha level set at 0.05 at the maximum at 5%, we find that my t-value of negative 4.94 lands right over here, roughly over here. So here is t negative 4.94. So it falls all the way over here inside of the region of rejection. So in terms of our statistic, that's good news because now we're able to identify if there are significant differences between smokers and non-smokers in terms of. So in our particular case, our statistic lands inside the region of rejection. So now the conclusion that we're going to be able to draw about the null hypothesis, because remember the null hypothesis had predicted that the difference between mu1 minus mu2, or mu1 was equal to mu2. In both cases, the difference would be equal to 0, or that t would be equal to 0, and that our statistic would not land inside the region of rejection. In this particular case now, we find that my statistic lands inside the region of rejection, so I'm going to reject the null hypothesis, and I'm going to now accept the alternative hypothesis, H1, that indicates that there was a significant difference between the two groups. So now here, if my statistic would have landed right outside the region of rejection, again, remember that we could always do statistical modifications to our data, and that we could have gone from a two-tailed test to a one-tailed test, potentially increasing alpha level if we were wanting to do that. But again, that's a dangerous kind of or a slippery slope to kind of get on sometimes. But in our particular case, our statistic lands in the region of rejection. I've now rejected the null hypothesis. I've accepted the alternative hypothesis that there is a significant difference between the two, and now I look at my research hypothesis, because remember, my research hypothesis predicted that smokers would perform lower than non-smokers, and in our particular case, we found that our prediction is supported. And why did we find that our prediction was supported? Because remember that for smokers, their average was equal to a value of a 3.8, and for non-smokers, we found their average equal to a 7.6, and we identified statistically that the difference between these two values, which comes out to being a t-stat of negative 4.94, lands inside the region of rejection based on our criteria that we've stipulated for a two-tailed test with a sample size of 10, degrees of freedom 8, and an alpha level of 5%. We've now identified that there is a significant difference between the two, and we're able to conclude. So we are able to conclude then that we were correct in our prediction that smokers would perform worse on the exam than non-smokers. Now, this seems like a very, very long process to be able to answer our question in regards to does smoking have an effect on exam performance? And here, based on our prediction that smokers would perform lower than non-smokers in terms of the exam, and the answer to that is yes, that is a very long process, but yet this is the process that we take in statistical testing. Now, granted, there are computer programs that will do this in a fraction of a second for us once it is that we've entered the data, but it's important for us to understand the conceptual and also the application purposes associated with our t-statistic. So again, now just to kind of wrap everything up associated with our t-stat, remember that the purpose of our t-statistic is to compare two mutually exclusive groups in the case of an independent samples t-test, and we're able to then identify if there are significant differences between our averages, in other words, between our sample groups that we've tested based on our research question and our research hypothesis that we've created for our specific situation. Now, please make sure to go ahead and review this particular lecture. I will be posting up a very brief mini lecture associated with repeated samples t-test, because essentially it's very similar to what we've already talked about. The formula just changes a little bit and the interpretation changes briefly because of the specifications associated with it, but yet it's still very, very similar to it conceptually.